Hi, everyone. My name's Krista Pellet, and I'm the Vice President of Minerals at Geoscience BC. And I'm pleased to welcome you to the 2022 Community Open House for our Central Interior Copper Gold Research Program. I'm joined today by Dr. Diane Mitchinson, who's a Research Associate at the Mineral Deposit Research Unit at UBC, specializing in integrating geology and geophysical data, and Dave Sacco, who's a Senior Surficial Exploration Specialist at Palmer. Joining me behind the scenes today from Geoscience BC are Brady Clift, our Manager of Minerals Projects, and Richard Truman, our Vice President of External Relations. They're both working behind the scenes to make sure this all goes smoothly. I'd like to acknowledge today that I'm speaking to you from Kamloops, which is in the traditional territory of the Kamloops to Secwepemc. I'd also like to acknowledge that the Central Interior Copper Gold Project that we're talking about today, or CIGAR as we more commonly refer to it, covers many traditional territories within central BC. Geoscience BC encourages anyone considering staking a mineral claim or conducting any type of mineral exploration work to engage early and engage often with the appropriate local Indigenous groups. A few housekeeping issues before we launch into the project update. First, please keep your microphone on mute. Rich will ensure that that happens during the presentations, but that will allow the presentations to run smoothly and allow all the attendees in attendance to be able to hear the information being presented. Second, we have time for questions following the final presentation. You can drop questions into the chat at any time, or following the final presentation, use the raise your hand feature and we will turn on your camera and microphone. I'll review these options again once we get to the Q&A session. A little bit about Geoscience BC before we launch into the CICGR updates. Geoscience BC is a not-for-profit society which provides independent public earth science research and data about BC's minerals, energy, and water resources. This research improves our collective knowledge of BC's geology, can be used to inform responsible natural resource development and investment decisions, catalyzes socioeconomic opportunities, and stimulates innovation and development of geoscience technologies. Geoscience BC supports many different types of projects, including those that identify critical metal and mineral opportunities in BC, those that measure or focus on reducing emissions, projects that improve our understanding of water resources, or those that build capacity, understanding, and partnerships, and support Indigenous involvement in geoscience research. Earlier this year, we launched Geoscience BC membership. If you've already joined us, thank you. If you haven't already, I encourage you to join as a corporate, individual, student, or associate member. Geoscience BC membership makes it easy for a wide range of partners to provide more input on and benefit from Geoscience BC research and project ideas, research priorities and project ideas. It also brings together industry, academia, communities, Indigenous groups, and governments to achieve shared goals and increase the impact of Geoscience BC research. To join Geoscience BC, you can visit www.geosciencebc.com/membership and fill out the application online. The QR code that's currently up on screen will take you back to the membership application as well, and we'll be putting this up again at the end of the session. And now on to the project updates. The CICGR project focuses on a group of rocks geologists refer to as the Quesnel Terrane in central BC, pardon me, roughly between Williams Lake in the south and Mackenzie in the north. This area has long been a focal point for Geoscience BC research, with known copper gold deposits to the north and south of the project area, but with a gap in and around the Prince George area where the bedrock is extensively covered by glacially deposited sediments. Way back in 2007, Geoscience BC created our first major research initiative, the QUEST project, which combined regional geophysical surveys and regional geochemical sampling and reanalysis programs to produce new public geoscience data sets that could be used to support exploration as well as improve bed mapping in the region. Since then, many of our projects have continued to look at this area. Back in 2019, Geoscience BC's Minerals Technical Advisory Committee recommended that there was still more work to be done to improve our understanding of this area, help focus exploration and investment, and support more informed resource decisions. The CICGR project was funded with an initial two projects, one looking at the surficial geology of the region, which is what Dave will be talking to you about today, and one using the existing geophysical data to produce new geological interpretations, which is the topic of Diane's presentation. As with all of our projects, First Nations, community, and mineral sector planning and engagement was key. Most of the project results that will be discussed today are already published and available through our website, with the rest to be published later this summer once results are received from the analytical labs. A reminder that Geoscience BC project results are public and available for free and can be used by communities, governments, Indigenous groups, as well as industry. And with that, I'm going to turn it over to our researchers to present updates on their projects. First up is Dave from Palmer. Once Dave is done, he'll turn it over to Diane from MDRU. And just a reminder that you can drop your questions into the chat at any time, and we'll answer them at the end of the session. Over to you, Dave.
Thank you, Krista. 1 second to get my screen up here. Okay, are we seeing the right slideshow? Okay, thumbs up. Well, thanks everybody who's joined. As Krista said, my name is Dave Sacco. I'm speaking on behalf of Palmer, who was a part of this project, and also Wayne Jackman from Noble Exploration, who participated in this. So I'm going to just give you an overview about the Surficial project that Krista gave us a bit of an intro on here. Sort of what the goals of the project were, and really why it was necessary in this area. So a little bit of a project understanding. It was a Geoscience BC funded project. So thinking about who did this, Geoscience BC funded this project. It was completed by Noble Exploration, as I mentioned, Wayne, and Palmer, which is the company I work for. We've collaborated on numerous projects before, most recently Trek, which was another Geoscience BC project, and also independently the Quest project that Krista mentioned earlier. So Wayne and I have been involved with Geoscience BC for a while, and it's been a great way to get public data out, high quality public data out to the explorers out there. So what is the Surficial exploration program? The main idea of this is to provide comparable data. So over a large region, you could get data sets from various sources that don't necessarily talk to each other well. So one of the big ideas here is to get comparable data out there and really help focus exploration in an area where there's a gap between major deposits. So if you look on the screen here, we've got Mount Milligan to the north, we've got Mount Polly to the south, and there's really a gap of deposits in here. And the reason is largely that there's thick sediments overlying the bedrock. So in order to work in these areas, we do have to consider these Surficial exploration programs. So where is it? I've already kind of pointed this out. So we've got Mackenzie to the north, we've got Williams Lake down to the south, and Prince George sort of right in the middle of this area. This is the larger CICGR area. And we are focused, the Surficial exploration programs are focused specifically on these little red boxes here, which are blown up on the right. And these are basically just divisions of area that were chosen because they expand from the previous work. So I mentioned Quest and Trek. We've got the Trek project down here in purple and the Quest project over here in yellow. So they expand from that. So again, the idea of expanding this continuous data set, and also because they were suitable for the sort of work we were doing. We are looking to collect till samples or a certain specific type of sediment sample, and these areas are well suited to that methodology. As well, we obviously focused on prospective geology, so looking at the bedrock in the region and saying, where is the most likely place that we need this data, and avoidance of private land. There's a lot of farmland, ranch land, developed areas sort of in this region scattered throughout, so we avoided that as best as we could as well. Why? We've already kind of talked about this a bit, but really the thick sediments that obscure the bedrock. So classically, you can go out, you can see some bedrock, you can knock some pieces off it, send it to the lab and see what's going on there. But with these thick sediments that occur specifically in this, in this whole basin area here, it's difficult to apply these classic approaches. So yeah, we're bringing in the Surficial strategies. And how is this done? There's really three main components to the project. The first was a series of Surficial geology and exploration focused mapping. That kind of gave us the foundation that we needed to complete the project. The second was looking at what data was out there and basically compiling and whatever data we could, or whatever sediment archive samples we had, reanalyzing those so that they're basically brought up to the modern level of analytics and comparable with any new data that is being developed. And lastly, the collection of new data. So once we see where we should be focusing and what the existing coverage of data is, we go in and infill those to again try and complete that full picture or provide that full coverage of data. So I'll go through those three steps in a little bit of detail here. So first off was the surficial geology and derivative mapping. So a surficial geology map, essentially what it is, it just tells you what type of sediment is, where it's distributed, and what processes may have affected that sediment. For us, we're targeting a specific type of material, so knowing, is that material around? Has it been affected by some sort of process in the natural environment, be it landslides or glacial outwash or something that may affect our ability to sample it or our desire to sample it even. And really what the surficial geology map does is it gives us that foundational understanding. And from that, we can derive maps that are going to help us understand the landscape from an exploration perspective. So here we've got the till sampling suitability map. And essentially this is reclassifying the surficial geology map into a relatively simple to read where are good places to sample, where are bad places to sample, where are we going to go and it's going to be really easy, where is going to take a little bit more effort, and where we just might not go in general because the material is not there, we may have to consider a different method. Another part of this map series was the drift thickness mapping. So the drift thickness mapping, again, it's a reclassification of the surficial geology mapping to give us an indication of how thick is the drift in any given area. And this informs a few different things. If there is bedrock mapping initiatives going on, mapping and sampling, prospecting, it tells those people working in those disciplines where they can go and actually find bedrock. It also informs where it's shallow, where the bedrock is shallow, and where the bedrock is very deep, and you may need an excavator or a drill to get into. So there's several classifications of drift thickness, and depending on what the area of interest is classified as, it gives the users an understanding of what it's going to take to get to the bedrock. It also helps us understand from a surficial sampling perspective what methods we might have at our disposal. In very thin areas, we're probably just sampling from surface, but as the drift gets thicker, we can get more information from the subsurface, and maybe sampling at deeper depths is going to be important. So with the map sets, this basically gives us the information we need to develop the field program, to understand the existing data, and then looking forward, if somebody is interested in an area, they can pick up these map sets, they can look at where the property sits, and they can get an understanding of what methods are going to be suitable for exploration there, what kind of challenges they might be up against, and what kind of advantages their areas may have. So the next portion of the work we did was the compilation and reanalysis of existing data. So these data sets were typically government surveys or Geoscience BC surveys. So you can see on the right here, I've got these purple dots, and these represent samples that were collected by the GSC in the sort of early to mid 90s is about when these programs were going on. And they would have archived a portion of their sample and stored it in their dungeon below ground. And the yellow dots here are from the CREST program. These were samples that were collected about in the 2008 to 2010 range, I think. I should remember this. This is part of my master's work where this occurred, or maybe I've intentionally forgot it. I'm not sure. But these samples were collected and also archived. So we took a split off the sample, and it was stored incidentally also at the GSC facility there. So the green dots here that I'm showing you, this is the Trek survey. So this was very recent, this is just a few years ago. And this is sort of the standard that we're working up to now. And the analysis that we use in the Trek survey is the same analysis that's going to be used in new government surveys. So all of these public data The idea is, again, to get them all comparable. So not to get too far into the weeds of things, but there are numerous different analysis protocols that the samples go through. So there's really a whole suite of information available for explorers to use, from your typical ultra-trace ICP analysis. We've done both the clay and the silt fraction of the samples. The major, minor, and trace elements. So this is referred to as whole rock sometimes analysis. And and essentially bringing all these up to the standard. So some of these data sets have some of the analytes done and some don't. So there's a different analytical protocol for each of these data sets I'm talking about here. We did have some issue retrieving some of the samples from the GSC, and this is because COVID hit. Basically, as soon as we started this program, we've now gotten access to the facility again, and there are about 574 more samples available to us. So I've shown those here. They're the dark purple dots. So extending that coverage quite a bit. And again, there's a series of archives, and until those are actually dug up, we don't know how much sample material is there, or whether they actually occur in the archive if they are still there. But we're hoping to get the majority of these samples retrieved and off to the lab relatively soon, to again just extend that data set out a bit further. So now moving on to the third component, which is the new surveys. So these are geochemical and mineralogical surveys. So we're targeting a very specific material type. It's subglacial till. The reason we target this material type is because it's a first derivative of bedrock. So compositionally, of the sediments that we have access to, it's the closest representation of bedrock we have without actually getting the bedrock. So from an exploration perspective, we know that it's a similar composition to the bedrock, and we understand how this material is displaced in the environment. So when we see anomalies in this material, it's relatively easy to understand the transport and where that anomaly source area in the actual bedrock is. We collect two types of samples, one for geochemistry, one for mineralogy. Geochemistry samples are relatively small. We collect those at every site. The mineralogy samples are about 10 kilograms, they're a little bit bigger. We collect those at about half the density. We also collect a bunch of pebbles from that material as well, just so we can get an understanding, like seeing the actual bedrock. The pebbles are dry from the bedrock and then kind of ground down a little bit, so we can actually see the lithologies that are within the area and use that for provenance studies. Target sample spacing is roughly 2 kilometers. So the idea with this is really to what we're trying to do is get 2 or 3 anomalous samples that say this area is interesting and worth following up on. These are regional surveys, so they're designed really to identify small anomaly clusters, or wide-spaced anomaly clusters, I should say, where more focused work is supported. As far as the sample design, probably not super important, but essentially we do try to design the sample strategy in such a way that we get the most bang for our buck as far as coverage, and also staggering things to optimize our potential of hitting, of collecting a sample within an anomalous zone. The samples we collect need to be below the soil horizon. Soil development changes the geochemistry of the sample, and because we want this to reflect the bedrock, we've got to get certain depths into the material. Typically, a meter and a half is sort of the minimum ranges that we're going to. The sampling is largely done with conventional methods. So this material we're after is it's very hard. It's incredibly hard. Excavators have been broken digging through this material. It's compacted by a 2-kilometer ice sheet flowing over the landscape. It has boulders in it that are just jammed, wedged in there. So digging through this material, if you were to dig a 1.5 meter pit in, the good material, and the rule of thumb is kind of the harder it is to dig, the better sample material is. It takes you a good half a day just to get down to the depth you need to be before you start sampling. So obviously not a very effective way to go about it. So what we do is we use opportunistic exposures. So regional program, we've got a little flexibility where where we can collect these samples. So we'll drive the road network. We'll see where these opportunistic exposures, typically road cuts or stream cuts, that sort of thing. And the actual sample site is going to be dependent on where we have an exposure and when that exposure is in till. And conventionally, we use hand tools for this. So when we're digging our holes, and then we dig another hole, and we dig some more holes, and then we spend a lot of time with our heads in the holes, and it's a long process, but because this material is so hard, but it works at a regional scale relatively well. But we do have some compromises in sample location, because we can really only collect these samples where there's an exposure and where that exposure is into till. So we had the opportunity on this program to test some purpose-built tools that would help us collect those samples, and with the real idea to improve sample distribution, allow us to plan a little bit more. So if you recall that Surficial geology map or the till sampling suitability map, we can look at the road network, we can look at the till distribution, and we can pre-plan those sites in that staggered grid that we want to have without the need to drive up and down the road networks to identify those locations, which increases the field efficiency. And this also gives us an opportunity to collect the material below, to collect till below other materials. So the system is, it's a very small drill, it's field portable. The idea of it is to rapidly collect samples at the depth we want to get. And an important aspect of this is we do collect an in situ sample. So it's a small core that comes out of it, so we can still ensure that we are collecting the right material, because when you're doing any kind of surficial exploration, knowing that you've collected the right material is really important, because different materials are going to have different geochemical properties, and you may think there's an anomaly, but it's actually just a different type of material. So we're very strict about the materials we collect. So I mentioned we got to test this. It was an excellent opportunity to see how you integrate this sort of tool into a regional program and what sort of benefits or complications it may have or pose. So we focused the testing in an area that we had visited in 2019, and really we didn't get the results we wanted. So you can see on the map here, the yellow dots are showing the conventional method of sampling results, or the results from the conventional method of sampling. There are plenty of roads moving through here, so access was reasonable. The issue and why we chose this area is because it presented a lot of the issues that are typically go hand in hand with their conventional methods. So lack of existing exposures, so road cuts or stream cuts, that sort of thing. And also there's a glacial lake that occurred in this area. So we had veneers of glacial lacustre material over top of the till that we were looking for. So a lot of, as we get into the oranges, this is the till sample suitability. Dark green being very suitable, moving into the red being not very suitable at all. You know, the light greens into the oranges, these things are less suitable because of that glacial lacustre influence. So we wanted to see, are we able to improve that? And in fact, we were. So the red dots here are where we were able to collect samples with the talon. So it's actually pretty staggering, the difference that having the right tool in these different environments provided. And again, the reason that we're in this region is because standard exploration methods don't work very effectively. So we needed to come up with a solution that would allow us to extend our typical approaches into these areas that aren't necessarily suitable. So we doubled the coverage. We were able to get the distribution we wanted again, because we weren't reliant on those opportunistic exposures. And sampling times were not heavily affected. They were roughly the same. And yeah, so it was, the results were very good. The coverage was very good. So just a quick progress report. Where are we? So the Surficial map series was just recently released a couple weeks ago. So for each one of those areas, there are 12 different areas we worked in. There are 3 different maps. So the Surficial geology map, the drift thickness map, and the till sampling suitability map. So these 36 maps are out there, or they're on Geoscience BC's website. They can be downloaded, and they're all geo-referenced. You can bring them into whatever software you use and get an idea of your area of interest, if it's covered your area of interest, what's going on there. The reanalysis portion of the project, the compilation, is about as good as we can get it. The first batch of archive samples, oh, I got another slide for this. The first batch of archive samples, so that's the yellow samples and the light purple samples, they've been released already. That data is out there and available and now comparable with the TREC data that's existing. And then the second phase, the dark purple samples here, we're just at the point of retrieving those samples. We got a call last week that they're heading down to the dungeon to get those out. So we should have those pretty soon. And then they'll be off to the lab and analyzed, and those results should come out shortly after. The new surveys completed. So these were completed in 2020 and 2021. They were finalized in 2021. Everything was sent to the lab. That's these pinkish dots in our focus areas here. Pretty good coverage in these areas, definitely extending things out. Those results just came back from the lab, and we will be compiling those and setting them out for hopefully an early summer release. And yeah, I think I will, at this point, I'll turn it over to Diane, and she can go on with her talk. And then I think we're going to open up for questions after she's done. So thank you, and off you go, Diane.
Thanks, Dave. Can I get a thumbs up from Dave that you can see my screen? You're the only person I can see right now.
It's good, Diane.
Okay, thanks. First of all, thank you to everybody who's attending or listening, if you're watching this online later on. My name is Diane Mitchinson. I work at UBC in the geology department there, and I'm a researcher in the Mineral Deposit Research Unit. And so I'm going to talk a bit about the project that I've been working on, which is the identification of new porphyry potential undercover in central BC. And this is the second project in the Central Interior Copper Gold Research Project. And I'd like to thank Geoscience BC for supporting this, and MDRU and all of MDRU sponsors, and also my colleagues who worked with me on this project. Okay, I'm just trying to change slides. Come on. Here we go. So the idea behind this project, and Dave already alluded to this, is that in central British Columbia, we've got a very prospective region for copper and gold deposits. And there's a belt in central BC called the Quesnel Terrane, and there are a lot of copper and gold porphyry deposits in this belt. Some that are being mined, others occurrences and showings and things. And you can see these yellow diamonds and white circles are copper gold occurrences or showings or prospects. And same down in the southern area. And then we've got some mines, Mount Poly, Mount Milligan, and there are more to the north and to the south of those as well. And then in the center, in the project area here, the same project area that Dave spoke about, there's a lot of this surficial sediment. And so you see there's a big break in these copper gold showings and occurrences right here. And it's not necessarily because there's no copper gold deposits in there. It's because it's difficult to explore in there. So there hasn't been as much exploration as there has been to the north and south of this area, and that's why these projects were put in place. So the question is then, what can we do to help explorers understand more about the geology underneath this cover material, and to help them understand the best places to go geologically to find more mineralization? So one thing we can do is look at geophysical data. So geophysics helps us to see geology beneath cover, or at least we can look at the geophysical data to try to interpret the geology under cover. So these two maps here show data sets These were 2 surveys that were commissioned by Geoscience BC and industry. An electromagnetic data set, electromagnetic survey, and a gravity survey that were done as part of the Quest projects. And you can see there's lots of interesting detail in these data, the electromagnetic data and the gravity data underneath this cover. So that's telling us that there's some interesting things going on with the geology and telling us a little bit about what the geology might be underneath there. So electromagnetic surveys give us information about the conductivity and resistivity of the rocks, and gravity data gives us information about the density of the rocks. And then we also have Natural Resources Canada magnetic data. So that covers all of BC. It's a great data set. It's a regional data set. Covers most of Canada, in fact, and that's a 3rd data set that we're going to, we applied for this project. The objectives of the project, and basically the outline of this presentation, was to use first the magnetic data that we have to identify some regional scale targets that look like the types of rocks that typically host these copper gold deposits. And then the second step was to model the sedimentary cover, the drift thickness using the geophysical data and other data, so we can get a sense of how much cover is above these rocks. And the third thing was to model the targets that we've come up with in 3D using geophysical modeling methods, and then to rank the targets based. Okay, so I talked about picking initial targets and what were we targeting. So this gets a little bit into the geology of the area, but basically we decided to focus on looking for alkalic porphyry deposits. So these are gold-rich copper deposits, and they're pretty unique to BC actually. And we decided to target porphyry deposits similar to ones that you see in the southern Quesnel. So this is a map of the southern Quesnel terrain. So it's kind of between Quesnel, which is just off the map, in the top, down to Princeton area. And so there's sort of a belt that within which sits several porphyry copper gold deposits, including Mount Polley, New Afton, Ajax, Copper Mountain. And so we decided that was going to be the type of rock that we're going to try to look for with the geophysics. So you can see this little belt tracks right up, and this goes right into our project area. This is the bottom of it here in the little green box. So we think perhaps we might have these similar style of deposits in the central Quesnel terrain. And the most important reason we decided to try to look for these deposits and these rocks is because they have a nice consistent geophysical signature. So we thought that would be helpful for us to find the types of rocks we're looking for. So what does a geophysical target look like for these kinds of deposits, or the host rocks to these deposits? I said they were they had sort of a consistent geophysical signature. So first of all, in the magnetic data, so if we look at some of these mineral deposits in the southern Quesnel, so the New Afton Ajax deposits and the Copper Mountain deposit, the rocks that host these deposits are pretty consistently magnetic, and that means they contain magnetite. So this was a nice consistent pattern that we could use to look in the central Quesnel terrain. Again, this is New Afton and Ajax and Copper Mountain. And now the gravity data, it's a little bit more coarse, so it's a little bit less detailed, but somewhat consistently, we have gravity highs associated with these host rocks to these deposits. Now, it's not as consistent as the magnetics, and there is some variability in the gravity, but overall in the southern Quesnel terrain, the host rocks of these deposits are associated with gravity highs. So we have sort of these consistent geophysical patterns that we can use to look for these rocks in the central Quesnel terrain. So picking some of these initial targets. So we started with picking these targets, and then we sort of followed up as the project went on to learn more about these targets. So we broke it into 3 blocks: the Fort St. James block in the north, Prince George block surrounding Prince George, and Quesnel block down in the southern end. And basically we we picked targets that looked like host rocks for porphyry deposits based on what we understand about their geophysical signatures. So we use magnetics here to pick these targets. And so they had to be roundish, because these are the types of rocks that host these are intrusions, and they usually sort of had a rounded or blobby sort of shape to them. And we wanted them to be sort of cross-cutting other stratigraphy. So intrusions usually cross-cut other rock types that are that sit there. So they need to sort of cross-cut other patterns in the geophysical data. They need to be rounded. And they need to be about the same size as host rocks we've seen down in southern Quesnel, like those rocks hosting Afton and Ajax and Copper Mountain and Mount Milligan in the north. So this is just a close-up of the targets that we picked about 57 targets. And so the FSJ is the Fort St. James targets, the PG are the Prince George targets, and the Q are the Quesnel targets. Okay, we have these targets. So I'm going to sort of back up a little bit, and we want to try to look at the thickness of the drift overlying the area, so we can get a sense of whether or not it's worth following up on these targets. Is there going to be 400 meters of drift thickness above these targets, or is it going to be 50 or 10 meters or less? And that might make it more reasonable to pursue them for follow-up exploration. So one thing we found was that in the electromagnetic data, the electromagnetic data were modeled by a company called Mirror Geoscience back in 2009. And in these models, so this is a cross section of electromagnetic data model, you can see the cover rocks are conductive, so they're red. They show up as red. And so we use this to interpret the thickness of the cover rocks on all of the lines of the EM data that were done in the survey. This was a really amazing resource for looking at the thickness of cover material. So this is just sort of an idea of how we might have interpreted the thickness of the cover there. So we combined the information we took from these electromagnetic data interpretations with some other data like outcrop. So if there's outcrop been indicated in previous mapping, that means there's no cover there. And then we found some information about how thick the cover was from drilling and water wells. And those are in the greens here. Outcrop is in pinks. And then the water wells and drilling are in greens. And so we know how thick the cover is in those areas. And so we added to that interpretations along all of these lines from the EM data. So we were able to fill in a lot of areas where we didn't have information previously about the cover. And then we interpolated the data set to find the thickness of the cover. So this is a map, a drift thickness map at the regional scale. On the right here is the whole project area. And then on the left is this sort of zoomed in area in the red box. And so you can see the scale here, the thickness of the cover extends from our modeling up to around 400 meters. And that's the very darkest dark blue color to black color. And then the pale colored areas are where the cover is thin. So it was interesting to see that there's quite a lot of variability in the cover, and we were able to add information to some areas, see where this red star is. If I go back, you can see this is this area where we previously had little information about the cover. And then we added information from the electromagnetic data interpretations. And we were able to fill in this area with information about how thick the cover material is. So this might help in terms of guiding explorers to areas where we might be able to get glimpses of the bedrock underneath the cover, or it may not be too far to drill before you get to bedrock to find out more about the geology in the area. And so also you can see here, we were able then to use the thickness as criteria for each of these targets. So now we have sort of an idea of the average thickness above each of these targets. Okay, so back to the geophysical data again. So I mentioned we did 3D modeling of the magnetic and gravity data. So we took all 57 of these targets and we used magnetic data because every one of these were magnetic bodies. And we used magnetic data and we did some geophysical inversion modeling. So that generates a 3D model of what's in the earth that causes that data. So we have 3D models for each of these targets. And then we have 3D models for from the gravity data as well. And from that, we can get the magnetic susceptibility of each of the targets and the density of each of the targets. That helps us to understand what the composition of these targets is in terms of their lithology. Okay, so we were able to build these geophysical profiles of these targets. And so basically, this here is a map. It's a slice through the gravity inversion. So it's a slice through the density model. It shows the density of the rocks, this background. And then you can see each of these targets that were picked, the magnetic targets. And this is the 3D bodies that were modeled from the magnetic inversion modeling, magnetic data inversion modeling. So each of these targets are magnetic, but they vary quite a bit in density. So if you remember, I mentioned earlier on that most of the host rocks and porphyry deposits in the southern Quesnel terrain had a gravity high associated with them. So they were dense. So these targets that are in red and yellow are the ones that are the higher density targets and the ones that are most like the ones in the southern Quesnel terrain. The ones that are blue are low density, and they are least like the ones in the southern Quesnel terrain. So these are magnetic targets, but they're not high density. So these are a bit different than what we are looking for. And I can't say whether or not this may still be a good target, but it's just not a lot like the ones in the southern Quesnel terrain that we know host mineral deposits. And I wanted to encourage people to, if you wanted to know a bit more about each of these targets, to look in the report, and we sort of explain what these sort of low density things could be and how they might differ from the high density things. So essentially, overall, they've got a lower density mineral composition. So here I've got a table. So for each of these blocks and areas, exploration areas, we have these tables showing the geophysical profile or the magnetic susceptibility density, the average overburden thickness or cover thickness above each of these targets, and any land features of note that we could find. Now there's certainly probably more features that should be noted if you're actually going to go out there and explore further on any of these targets. But we've noted rivers and roads and First Nations reserves, buildings, anything that we could see in the data, in GIS data, lakes. So I just can quickly go through and show you, these are sorted with the highest density ones on top. So the most like host rocks in the southern Quesnel terrain. So we've got two very high density ones that would have very high density minerals in it. The reds are high density, and the yellows are sort of moderate density. So we're kind of coming down to the lower density and less like the southern Quesnel terrain porphyry host rock. So these are the blue low density ones that are not so much like the targets that are in the southern Quesnel terrain. So that's the Fort St. James block. This is the Prince George North block. We've got we got a couple of high density ones and then some medium density ones. So nothing very, very high density here, except for a couple, a little bit just to the north of Prince George. So these are the high density ones and the medium density ones. Southern Prince George. So this is obviously a very busy area. Prince George is just right here. We've got some roads going through. So we tried to note some of these things and whether roads can be a good thing. Sometimes roads can be a bad thing, obviously, but it might rule out some of these features, can certainly rule out some of these exploration targets, or some of the roads maybe are going to get you closer to exploring some of these things. So we've got some high density ones, some very high density ones, and some high densities, a couple of moderate density targets, and then one low density target. And the Quesnel block, we've got a lot of sort of smaller bodies in this area. And a lot of them seem to sit kind of on the edges of these, if you can note this sort of elongated dense feature in the gravity model. These, I believe, are associated with volcanic rocks, so not intrusive rocks. And it looks like a lot of these targets sit on the edge of these. So it looks like they kind of sit on the edge of geologic contacts. We've got a variety of things here, some just a couple of that are very high density, a bunch of high density targets that are similar to Mouse Mountain, if anybody's familiar with that, that deposit, and some moderate density targets, and then just a couple of low density ones. So we've got a lot of sort of moderate to high density targets in this area. I just wanted to make one note about the implications of scale here. So looking at Mount Poly, the Mount Poly deposit, Copper Mountain, and New Afton deposits. So the scale of these targets, I didn't mention earlier on, but the bodies are, say, 5 to 10 kilometers across. And so that's quite a large body. And I said we picked them based on the fact they're similar size to the host rocks of porphyry copper deposits in southern Quesnel. So if you look at the Mount Poly host rocks, the intrusive rocks in purple here, you can see this is kind of like 5 to 6 kilometers. There's a kilometer scale here across, and the actual mineralized areas are about 500 meters to a kilometer across. So it's just something to be aware of if you do decide to follow up on any of these targets. This is the host rock potentially to a mineralization. So the idea would be to look around this target and above this target to look for mineralization in sort of smaller, more compact areas of about 500 meters to a kilometer. So same with Copper Mountain. Here's the intrusion or the host rock to this deposit. Again, it's about 10 kilometers across. And then these are the mineralized areas where the pits are. So you can see the size of the pits are about a kilometer. And New Afton, you can see just the edge of the host orange here, the host rock. And then the pits are less than a kilometer. So this is just an idea of the scale of these targets. So these are the host rocks, and then the mineralized zones would likely be similar to these, so on a much smaller scale. I'm just going to briefly, this is a video, I won't play it, but the deliverables, there's a program you can download called Geoscience Analyst from Mira Geoscience, and I packaged up the different blocks into Geoscience Analyst projects, and it contains all of the targets and other information. And so the program is free. You can download it for free, the viewer, and you just turn on the project that I put together. And otherwise, I've produced a whole bunch of different deliverables that would work in different software that you might use. But this is a free 3D viewer. It's in 3D, and it's quite handy and useful for looking around spatially. So that's it. I hope that you find that presentation useful and the report and the deliverables. And again, as Krista said, please, if you want to follow up on any of these targets or anything like it in any other jurisdiction, please consult with First Nations prior to any work. Just a few more acknowledgements. Again, Geoscience BC, MDRU, Randy Enkin at the GSC, Baram Najafian, he's at MDRU, and he did a lot of rock prep for me. UBC GIF, the geophysics group that we worked with, and the reviewers for the report. Thank you so much.